My name is Amy from Nexcelom Bioscience, and I'd like to thank all of our attendees for joining us today for our Celigo user training webinar. The topic today will be how to capture bright field images along with viability images on the Celigo. It will be presented by Sarah Kessel. She's one of our application scientists and lab managers at the San Diego office at Nexcelom. I'd just like to remind all of our attendees that you will be muted throughout the duration of the webinar, but if anyone has any questions for us, feel free to type them into the questions bar, and I will read those questions out to Sarah at the end of the webinar, and we can have a Q&A session for you. Also, the session today is going to be recorded, so everyone who has registered for this webinar will receive a link to the recording via email, and you can watch the webinar over again, or you can pass that link along to a friend or colleague if you wish to share this content with them. So without further ado, I'm going to pass the torch on to Sarah Kessel to begin our presentation today.
Thanks, Amy. Hi, everyone. Welcome. So obviously you heard the title for today. I just want to give you a scenario where you and when you might use this type of application. So you've been running proliferation bright field images in a growth tracking fashion. At the end of that experiment, say it went for 5 days, you'll do a viability stain with Hoechst and PI. But that application is just 2 channels. So all your experiments prior to that were in bright field. And so now you kind of want to have not only your Hoechst PI staining, but you also want to have some bright field images. So that's when I want to show you how you can acquire your viability application images using 3 channels instead of just 2-channel application. So today we're going to cover how to use the, it's called the Target 1-2 plus mask application in Expression Analysis Suite, and we'll go over how you actually set up the Celigo from starting on the Scan tab, the how to acquire the images, making sure you have the right settings for focus and illumination, and then how to set up the analysis of the images so you can have proper segmentation, and then we'll cover the gating, which is a little bit new, and the results and reviewing of the data we'll cover at the end. And then we'll just do a review over what we've covered at the end. So the important part of this is basically again, you want to have a viability staining, but sometimes it's really important to recognize the cell morphology, as you see in bright field, can add a lot of interesting insight to your assays or experiments. So typically when you run a viability assay, you'll select the dead plus total in the viability suite, and that would just be your PI and Hoechst staining. But that doesn't give you any insight onto the bright field morphology. Some of these cells, as you'll see, have rounded up, but they're not dead. So that might be a value to you in looking at your drug screens. So I actually have in this plate that we're going to scan today, cells that were stained or treated with alpha TOS, which is typically vitamin E, and the drug treatment caused some cells to round out, but it didn't kill them initially. So one thing to note, a little education, in the application selection expression analysis, we're going to select the target 1+2 plus mask. This way, we're going to actually set up the channels as in this table. So target 1 will be our bright field image, and we're going to be looking only at the morphology. We won't be doing any analysis on it, but just having that bright field image to share will be important. And then target 2 will be our PI, our dead stained cells. So we're going to have the illumination be red. And then the mask channel is going to be the Hoechst stain, so that color will be blue. And ideally, the mask is what we're going to say is covered in every cell. So every cell has a nuclei, so we can use that information for identifying all of the cells. And so not all the cells are going to look that great in bright field, so we wouldn't use that as the mask. And not every cell is going to be dead, so we can't use that as the mask. But every cell does have a Hoechst stain, so that way we can use the Hoechst stain as our mask channel. And what does that mean? Basically, we're able to identify all the cells in the image using the Hoechst stain, and we'll draw an outline around the nuclei, the blue pixels, and that will be counted as our total number of cells. And in the other 2 channels, The cells may or may not have a red stain, but we can use that outline from the Hoechst stain to look at the red channel for any red staining of the nuclei or in the nuclei area, which is where PI would be found. And then if the cells are dead, the morphology of the bright field is going to look horrible, just kind of dead, shriveled up cells. So that way you wouldn't want to use bright field as your mask. But we can see how the cell morphology looks. Okay, so basically we'll use the mask hook to identify our cells and then look for pixel intensities in the red channel target too. So this would be the same kind of application if you do the GFP transfection efficiency. You could use Hoechst as your stain for all the nuclei, and then the second or the first channel could be a GFP signal, and then we could score how many cells are actually GFP. Today we're only looking at the PI. All right, so we've covered over the idea of the target 1, 2, 3 mask application. Now let's get into the Celigo software and show you how to acquire the images on the system. And then we'll cover how to analyze it. And then the gating tab is basically of the objects we find, how do we score them positive for PI? So here we are in the beginning page. We're going to click create a scan, and then we're going to list the 96 well plate, identify the Greiner 655090, that's the black wall clear bottom plate, and then we'll give our plate an ID that is unique. So I've already imaged this plate once, so we'll image it again with the same plate ID, and then we'll load the plate. The stage will open up on the system, and we'll put the plate in the stage and then move over to the scan tab. So here on the application, we're going to have the drop-down menu. We want to go not into the viability section, which I was saying before is just a 2-channel application, typically dead in total. We're going to move further down into the expression analysis suite. There it is. We have a lot of options, so we want to have this target 1 plus 2 plus mask application selected. All right, so the first thing we'll do is set up the mask channel with blue illumination and also set up the system to register the focus on this channel. So we'll switch over to the 3rd channel, which is the mask channel. Just click the mask. And now we'll set up the illumination, which it already defaults to blue, so that's fine. Let's click on a well that I know has content in it. So we'll go over to C2. By clicking the navigation button, it navigates and then click on the well to C2. And typically for fluorescent applications, I'll use the camera control snaps so I don't photo bleach my samples. And now at this point, you can barely see the cells. They're dim and a little bit out of focus. So first we'll fix the illumination exposure to about 50,000. Typically for Hoechst, I will turn the illumination between 50,000 and 80,000. So right now it's slightly out of focus. So let's just set up the focus first by clicking focus setup and then register auto. The system will move the images up and down in Z and try and find the best focus. And then it'll use the hardware focus mechanism to memorize that distance where the cells are in focus to try and reproduce that same focus across the entire plate. Now we can look at the objects to see if they're the right pixel intensity. If it's too dim, just turn it up to maybe 80,000. I'm looking for 150,000 or 150 pixel intensity. So now we'll switch over to the 2nd channel and set it up for the red illumination, which will be our PI, and then change the exposure. Let's see what it looks like first. Clicking snap will turn it, okay. 50,000 produces a pretty good pixel illumination value. Now let's just click find focus so it does a better find versus me just turning on live camera and trying to adjust the focus. I like to do find focus instead. It moves up and down in Z and produces where the cells are in the best focus plane, which is about 18 microns negative or minus from the blue channel. So we'll click set offset, and that will populate that number, -18, up into this box here. and that means the system will collect the red channel images 19 or 18 microns below the blue channel. The illumination looks pretty good at 50,000, so now we can move over to the first channel with the target 1 and set it up for bright field image acquisition. So it defaults to blue, so we'll switch it over to bright field. And then you could click Auto Calc. It would do a one-time adjustment on illumination, but sometimes when you have drug treatments in your wells, so you can see when you click Auto Calc, it produces a background intensity for bright field between 100 and 150. That's just fine, it works well, but when you have drug treatments, sometimes the drugs or the growth or death of the cells causes a media color change, which affects the background or the grayscale picture. So typically for bright field image acquisition, I like to use a different type of channel illumination acquisition. So if you go up to the top and you see it says custom channel, we're going to switch that over to auto exposure and gain channel. This is what I use most of the time for bright field image acquisition, and then just click apply. What happens is on every well, it will determine what is the best illumination for that one well to give a pixel intensity that's like in the range of like 135, if you want to say, really in the middle of the camera range. And it'll do that on a well by well basis. That means you have the same color background for every well. Next, we'll select the wells that we want by clicking the selection button and highlight over the map on the plate navigation, and then just click Start Scan. We now move over to the Analyze tab. And here's a little button that was present in the Scan tab, but I didn't want to focus on it yet. So here we can, in the Analyze tab, customize our channel name. So it opens up this menu and you can personalize the labels that are displayed on the screen. Instead of target 1, we can put in things that are more relevant to our experiment. So bright field, red, and blue. And I'm doing that for these two sections, channel and feature. Feature is the graphic overlay. And then the last thing is I want to change class 1 to dead because that's the population I'm interested in the report. So now you see here the image display labels as well as the graphic overlay labels have changed to what we've just customized it to. So you can see that we're collecting the images, and the wells will turn green on this little plate map. When you click on the well, it will populate one of the images collected in the well, but all 3 channels are displayed at once. And you can select any one of the green wells. Those are images that have been acquired and saved to the hard drive. You don't ever have to hit save, it just automatically saves it. So we'll just zoom in a little bit, and you can see how sometimes the cells, the morphology of the cells that are getting affected by the drug are rounding up versus their normal morphology, which is adherent and long. That might be interesting for you to understand that it goes through that process before it actually loses its membrane integrity when PI gets to stain, move in. So you might be looking at that kind of information additionally to your viability. Notice that it outlines the nuclei in the picture, so you can see even if I pick on the graphic overlay for the red channel, it matches the same outline as the blue mask channel, and that's the whole function of this mask application. The blue channel that we have selected as our 3rd channel, the mask one, the outlines for the other channels will be matching exactly the same. So you only have to set up that blue graphic overlay. You don't have to worry about the bright field or the red graphic overlay because it's automatically the same as the blue. It's a little bit easier. All right, so make sure you have your checkbox down at the lower left-hand corner for auto analyze. So every time we turn on a parameter or adjust it, it actually automatically updates. So I do turn on my well mask, and for 96 wells, I might pull in the well mask to be like 99 in case there's any edge effect going on the well walls. And the other thing I would probably do, my Hoechst looks a little dim. I probably should have turned up the exposure a little bit more. So to compensate for that, I'm going to turn down the intensity threshold. That means I'm going to be able to pick up dimmer nuclei. And then also I'm going to checkbox the separate touching objects. So those are the three things that I've adjusted: the well mask, the intensity threshold, and the separate touching objects. At this point, we can move over to the gate tab. So just clicking on the gate tab up at the progress or workflow, you move over to this screen and you can see the first thing we'll want to do is click on one of the green wells. That is an image that's already saved in the database. The system is continually collecting images for the rest of the plate while we work on some of the analysis parameters. So once you click on a well, you will see it's the whole well. So we'll want to zoom in with our scroll button on the mouse, and you'll see as the image becomes into the higher resolution zoom level, the graphic overlay that we saw before is now outlined in a color of royal blue. A little bit hard to see, but that's okay because we're going to be creating some gates that will be different colors. So this is the outline from the nuclei identification parameters on the Analyze tab in the Mask channel. So if we turn on the bright field again, you can see that there are some cells that are rounded up and some that are really long. You could create, what we're going to do right now is create a plot to identify just the total number of nuclei cells. So we're creating, we're going to click the green plus sign. It asks, what is your source population? It's all total. And that's because we're right there in the beginning. And then we're going to pick the plot type is the histogram. And then the plot parameter I first want to use is the area. So I want to get rid of any small or large non-nuclei items, debris. So click OK once you've selected area. And each of these outlines is now being plotted on this histogram according to its area. And so what we'll do is select the min-max gate up here at the top. And then we're going to click and drag the mouse from left to right, and it creates a red shaded area over the histogram of the area that I just swiped the mouse over. Everything in that area is now color-coded red, not only on the histogram, but on the image. The graphic overlay is now outlined in red. Anything outside of this histogram area is colored blue, our original blue. So that means it's excluded from this, this gate. And then you can move the gate by clicking the center and dragging it left and right to see if everything is lining up right as far as what's called a cell or debris is not excluded. And then the last thing we want to do on this graph is click checkbox total. So this is what I want my denominator to be. This is my new total. Next, we'll click a green plus sign to create a new plot. Notice this is the population total has moved to population 1, the one we just created. And we'll use a histogram again. And this time we're going to look at the red mean intensity. This is our PI stain. So what we're doing is going to create a histogram of all the objects identified in that red outline. We're going to plot according to the red pixel intensity from that red channel. So you can see this big spike here is actually our non-red cells. They are the live cells. So first I want to change the scale of this histogram so we can really focus in on that small population. So we'll change the y-axis. Instead of 3,500, let's zoom it into about 500 so we can expand and really see the two different populations in our image. So just type in 500. And then click OK or closed, and you'll see the scale has changed. And now it's really noticeable to see the two populations. So at this point, we'll use the splitter gate, which is the one that has a green and red little icon. And then click in the space between the two peaks. A red line appears and separates the population into a green and blue shaded area. We'll first adjust the color because it's a little hard to see. We'll change that aqua blue to a bright red. So that's going to signify this is our red population. So cells that have red pixel intensity color are on the right side of the graph, and also in the image itself, it is outlined in red. Typically, I will turn on and off the graphic overlay to see how did I score properly the cells that are dead and dead or not dead. And if I need to make adjustments, I can do so by clicking on the red bar and moving it left and right. It seems to be pretty good. Let's just check the box called dead. That means this population will be reported in the results tab. So here you can see if I wanted to, I just click on the red line and adjust the scroll bar or the location of the splitter. And as I do so, the graphic overlay adjusts its color to be scored accordingly. If you want to have a peek at the results for just this well that you actually have in the display area, you can click on the little word that's just below that. It's called results. You can see the arrows pointing to it. If you click on this, it's just displaying the results for this particular well. We're sitting at about 13.65% dead. And then just below that, it shows you your counts. And this is because we check box those two parameters. We gave it a new total and a new dead, and that's the percentage that's reported. If you're happy with the settings, then you just go ahead and click Start Analysis in the lower right corner, and then the system will proceed to apply the Analyze settings on the Analyze tab, as well as the gating parameters that we've just described into all of the wells on this plate. And then it progresses over to the Results tab. So you can see here that the system is still collecting the images, and now it should start reporting the results on the thumbnail. So currently you're displaying the bright field images, that's the first channel, but you can switch the thumbnail visuals to the red or the Hoechst channel if you want. And then the first measurement that shows up, here it is the percent dead, is also being displayed on the thumbnail images. If you want to change the parameter display to something else, you can do so by clicking on it. So as we progress through the image acquisition and analysis at the same time, you can see that I have a drug dose response that shows high killing on the left, and then it decreases as you go to the right. So let's double click on a well, and you'll see that we can see the high resolution image show up in the display area, and then the analysis parameters are showing on the left-hand column, the results for this particular well. So what's interesting is that we have 36% killing of the cells, but you can tell that just from the bright field morphology that they're not looking so good, that they're the ones that are not dead. So if this is of interest to you, I didn't include it in this webinar, but you could actually reanalyze the bright field images for rounded up circular cells that should normally be adherent. So if you guys are interested in knowing how to do morphology analysis on your bright field cells, I just raise your hand or note for something when we come to the end of this webinar, and we can I'll schedule or try and create another webinar on how to do morphology analysis on your bright field adherent cells for stuff like this. You can clearly see the cells are not happy. They're rounded up, but they're not dead. They're probably fine, but they're actually probably going to die in a minute. Anyway, so this is how you can showcase how bright field images add value to your, not only to your dead viability assays. So you're going to report you're dead, but you also have the ability to show that, yeah, that's probably going to be detrimental to the rest of the population in a short amount of time. So I've changed the color of the total to black because it's a little bit easier to see, but you can also see that here we're in more of a control well, that the cells have not rounded up and they're a lot more flattened out. There's a few that are rounded up, but it maybe not the end of the drug treatment. But we've still only got 3% viability or death going on there. Here's a control well. It looks very happy. So when you're doing your reports, you can produce your graph, the bright field image to show the cell morphology. Okay, so today what we've covered so far in the presentation or the video training is the new application Target 1 + 2 + mask, and how you can use the nuclei Hoechst staining as your object identification, and then look in the other two channels. Today it was for the red staining in the red channel for PI for dead cells, but you can also use the bright field image to add value about your morphological changes that happen to your cells before they die. So I found this to be more interesting from our customer's perspective. I'll teach them initially the 2-channel application, but when they see the added value of a 3-channel with the bright field, they end up going with that one as well. The gating tab was something I really wanted to focus on. I think that's kind of a little bit challenge for people that have never done flow before. So this is a good video to review if you guys kind of get stuck on the gating tab. Let's see. Remember, you can report up to 4 classes. We chose to do just 1 class today. So if you had done GFP, say, for instance, in addition to the red and bright field, you could have selected GFP as another class to report. The important thing I will note on the image acquisition, make sure you have good illumination for the fluorescence channels and a good focus also. So that's pretty much it. If anybody has any questions, I'd like to open up the floor for the audience to ask some questions.
Thank you, Sarah. That was a wonderful presentation. So as Sarah had mentioned, we are opening up this time to answer any questions that our attendees have for us today. As a reminder, all of our attendees are muted, so we cannot hear you, but what you can do is you can type in the questions into the questions bar, click submit, and then I will read out the questions to Sarah.
Amy, also, I forgot to put on this last page, if you guys have additional support questions that come up after this, you can always email us at support@nexalum.com, and we will get back to you as soon as we can. And even if you need to schedule an online session, first contact support@nexalum.com, okay?
Yes, Sarah, thank you for mentioning that, absolutely. So I will go ahead, Sarah.
I just want to reiterate, if you guys have interest in looking how to segment your cells for bright field in the morphology changes of rounded up cells, just email the support@nexalum.com to let us know that you do have interest in that, or any other topic that you want us to provide a video webinar training on, okay?
Thank you, Sarah. We do have a question that came through, so I'm going to read this out to Sarah now. Are other morphological changes in the cells other than rounding able to be detected and quantified?
So the parameters that you would see in the drop-down menu on the gating tab, one is the roundness factor. So that would be aspect ratio. Let me just get this back up. Aspect ratio is just length versus width. That would be the minimum and the maximum diameters of the cells. The second one would be form factor, and that's kind of more if your cells have more like a starfish type visual on them. That'll give you a different formula that calculates the form factor if you have a lot of protrusions coming out of your cells. So if that is something that is interesting into your cells parameter quantification, that's the second one you could do. Intensity maybe one. So let's see, if your cells are getting darker, you could plot your bright field cells according to their pixel intensity. Sometimes drugs cause cells to get darker. I don't know if they take up molecules or dark color stuff. That's all I can think of right now. Size might be another one. So sometimes like drugs like cisplatin, when it binds to the DNA, the cells can't divide, but it does physiologically get the cells to grow larger until it ends up dying because they can't support that size. That size differentiation might be of an interest to you to note. It's not killing the cells, but the cell got really large. So you could do a size measurement on your cells with drug treatments. What else? I think that's it for me that I'm thinking of.
Great. We do have another question that's come through. It states, do you need to expand the mask to include the rest of the cell beyond the nuclei to capture all the staining in the cell?
Well, it depends on the stain you're using. Today we used PI, which is a stain that will bind to the DNA in the cell in the same area that the Hoechst is stained, so that we didn't have to do any expansion of the graphic overlay for the Hoechst mask. But say you had a cytosolic or membrane-bound stain, then you could do a dilation of the graphic overlay in the Analyze tab. Or alternatively, you could use something like the merge application. I didn't cover that today, but that was another option in the expression analysis suite that allows you to get a little bit more pixel information beyond the nuclei area that was identified from the nucleus. If that's of interest, you would probably do a dilation for that. So an application specifically for that would be antibody binding assay. So you could use the Hoechst staining as your identifier and then do a dilation because your antibody binding might be on the surface of the cells. That would be one case you could do dilation. But this one, you didn't have to.
Great, thanks, Sarah.
Yep.
I'm going to give everyone a few more seconds to see if we get any other last-minute questions come through for us today. All right. Well, I'm not seeing any more questions come through, so that will conclude our webinar for today. Thank you everyone for joining us, and Sarah, thanks for a wonderful presentation. As a reminder, this session today was recorded, so everyone who has registered for this webinar will receive a link to the recording, and you can watch this webinar over again or pass the content along to a friend or colleague if you want to share that with them. As Sarah mentioned earlier, if you do think of any questions later on that you didn't propose to us now, you can always reach out to us at support@nexcelum.com. Email us, call us, we'll be happy to help you. Anything you need, we're here for you. Again, thanks everyone for joining. I hope everyone has a wonderful day.
Thanks, everyone. Bye.